Hello, I'm Chris Athenis. I'm a KMP developer, and we're going to go to the next video in our series about how to program from the ground up. Easy for me to say. Tech support said they're going to be coming out on Tuesday to close that thing. I hope they make it this time. Let's see. Okay, so we left off on the transistor, right? This little bugger. And now we're getting into the interchangeable integrated circuit. So the integrated circuit in 1959. So the big idea this guy came up with says that we can use photographic techniques to create thousands of transistors on a single chip and radically reduce the cost of manufacturing and assembly of computing devices and increase the functionality and reliability. So this guy, he made the jump because before that, these transistors were just materials. They were just glad to get the materials together. Those three materials, NPN or NPNP, they're just happy to have just that component. And this guy says, you know what? These are just layers of silicon and stuff. We can lay them down using different photographic chemical-ish techniques that have been going on for a long time that allow them to take a very large design and shrink it way the hell down just with photographs. So this is really actually very interesting and useful knowledge to know how this stuff works from the bottom, because all the mystery goes away.
The event that we're having today is a transfer of a lot of historic artifacts to the archives here at Caltech. It's a story that hasn't been told.
So this isn't the guy that invented it, the technique, but this is not him. But this is one of the guys that definitely took it to the next level.
It starts out in 1965. I was consulting for Gordon Moore at Fairchild, but I had known Gordon since 1959 and had consulted with him at Fairchild since it was a very small company. And Gordon always thought way ahead. He's a very, very big picture kind of person. And one day I came in and he showed me that picture. It starts out in 1959 with a single transistor. And this is one of the very first integrated circuits in 1960, 61, 62, 63, 64, 65.
Yeah, that was this guy.
And he showed me this picture and he said, you know, they're getting to make more complicated.
Well, it wasn't that guy, but it was the guy, one of the people that worked there.
Integrated circuits every year. So of course he's Gordon. So what did he do? He plotted how many transistors there were on each of those as a function of the year. And he made a log plot. Just the log to the base 2, of course, because it's Gordon, as a function of the year. And he noticed it's a straight line. And he just extrapolated that. And so Gordon made the leap of faith that you could make transistors smaller so you could put more of them on an area and they would still work. And also people would get better at the process by which they make these things, so the yield would get better. And if they could do both of those things, which was a huge if.
The yield means not all the chips that they made worked. Like most of them didn't work because these processes they were just still trying to figure out how to make this stuff smaller and faster and tinier and more reliable. And they were just experimenting all over the place. And some stuff worked and some stuff didn't. Most stuff didn't, let's be real honest.
Then the economics were absolutely compelling. And it was a week or two or so later. He said, Carver, you're working on electron tunneling. I said, yeah, that's right. And he said, now that's something that happens when things get very small, right? I said, yeah. He said, well, won't that prevent transistors from getting smaller than a certain size? And I said, yes, it certainly will. And Gordon said, well, how small is that? I swallowed really hard. I'll have to work it out, Gordon. I can tell you from what I know right now that the gate oxide isn't going to be real comfortable if it gets much below 50 angstroms. But I'll have to get exactly what those things are. The papers in the literature were full of all the things that were going to prevent you from getting smaller. So, of course, I puzzled over this. So 1968 was a watershed year. I had finally figured out a simple way of looking at the physics of Moore's law. And that was this little piece of physics. And the bottom line was that as you made the devices smaller, you had to scale the voltage down proportionally. But if you did that, the devices got faster, they dissipated less power, and everything got better. And the figure of merit, how much computation you could get done for a given amount of power, went like the cube of the scaling factor. So here we were.
Yeah, so there's not many things that have come across humans that as we apply effort in, the output goes by the cube of it. So it's like the effort times the effort times the effort. Just put the effort in, it goes effort out, multiplied on top of each other. So yeah, that's why we went gangbusters into this. totally transformed our society, transformed the way we looked at working, how we, the whole thing. This thing blew up. I grew, I grew up in an analog area. I still had to dial a rotary phone and all that stuff. So I saw the whole transition to go to digital. So it's been quite uh, deep.
Long runway without changing anything except just making everything smaller. That was a huge aha for me. And what it meant was we were going to have things with millions of transistors on. No one had ever made a machine with millions of moving parts. And we were going to be doing that. And how in the world could you design a thing that had millions of moving parts and ever get it to work?
You have to have software. So they made a machine to write the program, to write the software, to make another machine. Because they can't. At some point, there's human limits, or like how much complexity you can deal with. So they wrote code to write the little traces.
But another thing happened that year, which was very inspiring to me. Barney Oliver, old Caltech alumnus, who was the chief technical officer at Hewlett-Packard, came down and gave a seminar. And what he did was he showed their latest calculator, and it was a thing of beauty.
Yeah, this is all discrete logic chips. There wasn't any microprocessors yet.
You could do all the scientific calculations with it. It had all the trigonometric.
It basically had all that stuff in there, but it was very specialized.
Functions. And it had a little space up here where you could put in a little magnetic card. It had memory for programs that were just sequences of the key pushes. And
a little piece of like tape, like I showed here. It would had a little card, one of these little cards, and it kept a little. Where is it? Where is it? I want to make sure this is like clear, because it's like, what is this? So here, this thing, right. Okay, so there's like a card that you use this kind of card. I guess we're like, this is computer stuff, and they put a little piece of tape on there, and they wrote a program in there like with this. So that's how they did that.
Of course, what it was for people like me to take our data and reduce the data. And this was the machine I talked to Bob Noyce and Gordon Moore about, and trying to convince them that this was going to be the future.
So Bob Noyce is this guy. Where is it? Here. This is the Noister.
Future. There was going to be something like that on everybody's desk. And this is what integrated circuits were going to be for.
There'll be more than that, buddy. But yeah, he was right.
Meanwhile, I was furiously learning how to design digital stuff. And I got pretty good at it pretty fast, because I spent every waking hour doing that. Well, the other thing I do when I get to where I understand it myself a bit is I teach a course on it. Because there's nothing like teaching a course that helps you master a topic. If you're going to teach a course, you have to build something real. So I chose the calculator, because a calculator is the thing everybody understands. At that time, electronic calculators were just getting popular because they were getting affordable. And yet they were complex enough that they exercised everything that you needed to know about digital logic.
And to do it Turing complete, which is, having this instruction. It's, we'll get into the Turing complete business of it. But basically, you can create a calculator function without doing all the Turing complete stuff. But if you make it Turing complete, a calculator is super easy.
They weren't a computer, but they were close. So this is a picture of me teaching a freshman class in digital logic, teaching about how you get data into a digital.
There's the little. See, it's very popular to teach this thing because it's super neat how it works. The 7-segment display and the input and the outputs and all that.
Digital system, and you'll see me here with my finger on a little keyboard. And it's a keyboard very much like the keyboard on the Hewlett-Packard 9100, that little calculator. You have to be able to get data out. You can see the display it has. Each position where there can be a number, there's a little thing called a 7-segment display. So each of these segments can be lit up independently. And here's A, B, C, D, E, F, and then G is in the middle. And these segments can be lit up to make all the digits. And you can.
I was like, what is this one right here? Okay, they don't consider this a segment, but it is a pin. It'll be the 8th pin, but there's 7 segments, and the 8th is the. That's very convenient how that worked out.
See that the number 1 has segment B and C lit up, and so forth. And we went through this in class, and we designed the logic circuit that went with each segment. And by the time it was done, when I press a key, it would light up the character. One of my very best TAs was a guy by the name of Richard Willis. He was just terrific. And we together hatched the idea that we should turn this course into a book and teach the very basic knowledge of how you reason through from something, a function that you want to create, to a digital system.
There it is. So that's the same one they use in the text in the sheet, and he shows the logic, just the Boolean logic sequence here down here for each one of the letters or each one of the numeric values. Here it is in BCD binary. Here it is in decimal. Here it is in BCD binary coded decimal, like all the digits. And then here's where all the segments, all the different segments. Segment A, segment B, segment C. Each one of these columns, and there's the numbers.
That's the absolute ground training you need before you design any of these integrated circuits.
See, exactly.
Intel
and computers in general. You just gotta know how this stuff works.
Was being hatched at exactly the same time as I was making this transition. In my head was always true that what I was doing was developing a way of thinking that was going to help with the design of very large-scale circuits, and I didn't know how. Every time I would go to Intel, I would go in and
he coined the term very large-scale integrated circuit. That's his term.
Talk to the people and see what they were doing. I watched the way they designed their integrated circuits. They designed the circuit diagram, and then there was a drafts person who would painfully, on a sheet of Mylar that was typically this big, that had little squares on it, would draw all 5 layers, one on top of the other, for the entire circuit by hand.
And that's why it took so long to develop all this stuff, because it was a huge corporations. They had a system in place. It was you just start here. This person does this person does that, this person. None of them really know how it puts together. So there was a lot of mistakes, a lot of errors. And that's why it took so long to get these things done until this guy came along.
Then that piece of Mylar was put on a light table, and on top of it was put a thing called ruby lith. Let's say that there was a stripe of the layer. They had to cut on both sides of the stripe and on the ends.
So these are the wires.
They did that for every shape on that layer. And then after that was done,
this is how the wires of the P, N, P, each layer was a P, and the next layer was an N, the next layer was a P, and each one of these things would lay down a little segment of this thing, which would be a little wire, basically a little wire made of that P material, N material, or just neutral material, just a little wire thing. And they would lay all that down with these photographic techniques. It's so crazy how they did this.
A pair of tweezers and peel out the parts that represented that layer. And then you would go check the whole thing. And then that ruby lith was used as a master at something like 200 times the
ruby lith. It's red. It's a layer that's got a little red ruby lith top.
Final size of the chip. Well, in order to get those lines absolutely straight, you couldn't do it by hand. They had a thing called a coordinate graph. It had effectively X-Acto knife blades in it. It had a knob on the X direction and a knob on the Y direction.
Human-controlled CAD. Holy smokes! They knew that this job had like 10 more seconds before they automated away with the machine that they're actually drawing. It's like, lady, do you know that you're actually sketching out your replacement? You know you're doing that right now? It's like, no, I have a good benefits plan. They really treat me very well here. This company's about to be out of business because of what you're doing right here.
So it was like an XY plotter, but you could set it by hand. So all the things you could do were Manhattan geometry, as it's called. I looked at this. I wanted to make these things. I wanted to design these things myself. I believed it was possible because conceptually it wasn't difficult. What was difficult is the way they were doing it. And they were the best in the field. It has to be a better way. So did anybody else make precision patterns? We had all of the aerospace industry around here that makes military specifications, printed circuit boards for circuits that went into aircraft and rockets and all that stuff. Why don't I find out how they make their circuits?
So without Carver Mead digging around, how many more years would it have taken for those people to realize, oh, there might be a better right now? They'd be doing it today. If it wasn't for guys like him, it's like, I just want to do it myself. And this is the kind of person that drives all of it forward, this kind of guy.
Good words. Well, it turns out that the way everybody made their layouts was to use a thing called a Gerber plotter. And there were commands for this. It was called Gerber code. And what it was you select a aperture, then you go to where you want it to start, you turn it on, you draw from one XY position to another till you're at the end, then you turn it off. That's not hard. So I started writing Gerber code. Well, I can't afford a Gerber plotter either, and it was a big thing. You had to have it in a darkroom, of course, because what you put down was Mylar that had photographic emulsion on it. It was basically a great big photographic negative. And then you drew one all in the dark. When it was done, you ran it through a photographic development process. So I couldn't afford to do that, and I couldn't have the time to do all that. Well, it turned out we're in Southern California. There are job shops that do it for the military people. You can hire a Gerber plotter by the hour. So I went down. There was one down in El Monte, and I went down and got to know the guy. He had his own little shop there, knew what he was doing. The Gerber plotter had logic in it, of course, to interpret all this stuff. It was individual transistors on circuit boards.
This is called bootstrapping, where you're using one thing and you're pulling up your boots, like you're putting on your boots by the straps. And you're like boots. It's called like bootstrapping, like the machine that creates the software, that creates the machine, that creates the software.
It was probably already 15 years old. That's when I learned you're always using the last generation of technology to make the next generation of technology. That's just the name of what you do. By writing a program, I had created a pattern myself that was precise. And I didn't need a light box, and I didn't need a draftsperson, and I didn't need a Rubylith, and I didn't need a coordinograph, and I didn't need a team of people to do all this. I could just do it.
So he doesn't describe. I'm sure he does someplace with this program, like what I'm sure it was written in Fortran or something like that at the time, because there wasn't much else. But I know he wasn't using assembly to write it out. But like that's quite an impressive feat, just by the way.
So this is what came out of the Gerber plotter that we would go and give paper tape to. So these are the contact pads. This is a metal layer, the blue one, and you can tell a lot from just looking at it. There's VDD, the power supply and ground, and then these are the drivers that are going to drive the pads. This
is just one layer of a multi-layer operation.
The pads that you make a contact to with a wire that goes off to inside of a package, which are the things you see that have integrated circuits in them. It's changed my life. Great. I knew there had to be a whole new way that had.
Right. So I just like zoom in on this here. So you can see the little wires on the pads. Each one of these pads is hooked up to one of these legs that's hooked up into the board that's hooked up into everything else. And that's how it's like this tiny little wire. It goes onto these pads on this chip. This is actually a little chip that they saw off that big piece of silicon. Yeah.
Integrated circuits in them. It's changed my life. Great. I knew there had to be a whole new way of implementing digital functions that was more regular, that was more structured.
Procedural. So exactly, because once these things, you have to have some sort of structure when you start to deal with hundreds of thousands of these things. You can't just throw them on there until it works. You got to have something else, and you got to have a tool that abstracts away a lot of this tiny little sketching out of all the little details, because it's just repetitive. It's like once you do one, it's the same thing repeated 55 times. That's why that lady's job is like, hey, you're not bringing a lot of stuff to the plate here, so you're about to get automated away. So anything that's repeated, repetitive, that takes like no thought, yeah, that's about to get automated.
Then what we now call random logic, just NAND gates and OR gates and flip-flops, and you hook them all together, which works fine for little things, but when you get to anything complicated, it becomes just a hopeless mess. So I had a student then, freshman, I'd been in my freshman logic class and was a super bright guy named Steve Polly.
And that whole concept of like starting off with one thing, does works at one scale, and then trying to scale it up to the next, 10 times larger or whatever, and it just falls over. That's called a paradigm shift. You have to enter a new paradigm. So he entered a new paradigm, as instead of using hand by hand, like logic gates all laid out by hand, he's like, well, let's use a computer to lay it out for us, and I just write a program that tells which chips I want to have, wherever, and it'll lay it out for me, and they'll do a way better job than I can in a more regular pattern and in ways that I don't have to think about all that cutting out of the little Mylar sheets. You do that. You do the cutting. I'll just do what to cut.
And I told him what I was doing, and I said, we can make these shapes, and we can make arrangements that will create logic functions. He got very excited about this. So we agreed.
And that's what those layers are. They're just the layers of the chemical, those NPN semiconductor materials on top of each other, clever patterns that do useful stuff for humans.
But I would write the code that would generate the artwork, and he would write the code that would take that same input, make a logical program from it that did the function of it. So that led me to the invention of the thing we now call the programmable logic array. It ended up, of course, that I wasn't the only one that had this idea. There was a guy down at Texas Instruments and another guy at Hewlett-Packard. We had all independently invented.
So that was just one style of doing before the computers were kind of thing. Is so you could have these sets of array or grid of these pre-made little chips, and you would wire them up, and each one would have a pre-made function, and you just wire them up in this in a chip form. They were just like basically blow fuses. That broke a bunch. So everything's connected. You blow the fuses and all the wires where you don't want it connected, and it would create these useful functions. And that's what he was talking about, the field programmable gate array. That's all it is.
Did this thing. That was a big aha for me. I can make a simple, regular arrangement that can generate any logic function. This structure then became a way of doing logic that I could realize I could do all the electronic design, I could get the timing right, I could do everything like that without regard to what exact function was being done. And then I could program that function later. So it became programmable. So I realized this is my version of Stan Frankel's LGP30 in miniature. It's a
So what he's talking about here,
my version of Stan Frankel's LGP30.
so what he's talking about here is basically like a little, like a sort of microprocessor sort of thing. Semi-micro, it's like rudimentary microprocessor. The next step is, of course, the microprocessor. So that's what he's talking about. Is like, I'm building this thing that's getting close to what we call a microprocessor now, before they really knew. And at the time, there was, of course, Defense Department programs that already blew past this a while ago, and were already putting it in the F-14 for their air control computer. And that was top secret for a long time.
In miniature. It's a finite state machine as realized in a regular structure that you can generate with a silicon compiler. So that was the inspiration for this, not just being a specific thing, but a very general way to do logic. So if you thought about it carefully, you could map the logic onto these very regular functions. And it ended up much later being shown that this actually resulted in a smaller and faster chip than doing it with random logic. It just opened my mind because I'm very close to the general purpose computer here. This is a picture of my first chip.
Right, he was like 1/2 step away.
And you can see the AND section here on the left. The very bottom thing you see.
Is he NAND?
And you can see the AND section here on the left.
Or just AND? Okay.
The very bottom thing, you see the storage. That was a shift register that had the number of bits that there were digits plus a couple.
So these are all little transistors in here. Transistor. It's all just transistors all over the place, all set up in these clever arrangements to do useful stuff. And he has them blocked out. And he used a little piece of computer software and said, take that image for the transistor and place it here and here and here and here and here and here and here, and then make it wire to here. Okay.
For the counting of extra. The white areas are the bonding pads where the wires come off to the outside world. Just for scale, I should show you what these chips actually look like. In order to have some illustration, made it clear what it was doing, I decided to program this thing to be a 12-hour clock. So it would display the seconds, 0 up to 59, and the minutes, 0 up to 59, and then hours, 1 up to 12. Because it's a general logic function. It doesn't care that there's a special case for 12 and 1 and all of that. It was just all built in the code. That's what all those ones in there are. They're taking care of the entire sequence. They're taking care of adding. They're taking care of making sure.
So what this is showing here is where all the little, I guess all the wires are all connected together. Yeah, it looks like that looks like what he's doing there. And this is the program for his field programmable gate array. So all the places where it's got a line, it's going to remain connected. And everywhere there's a gap, they've broken, blew the fuse, as they say. For that connection. So let me see, is there a section here that I want to, where he shows off the
Play the same chip in a package that's very, very similar to the ones that I put the chips in myself back in 1971. And it's being tested in very much the same way. There wasn't a setting mechanism built in the chip. I wasn't developing a commercial clock. I was developing a general purpose structure that this was a demonstration for. And to do that, you actually have to display the output. Well, I had built the chip to work with this little.
So this is now they're using tubes again for doing this display, this type of display that basically is right before they did LEDs came out. They had this technology that come a long way that they use. It's beautiful, but it's also very power hungry, and it's great that he brought out it's sort of like an XC tube, but it's not. It's another thing, another technology.
Fluorescent tube. It was designed in such a way that the chip could drive the signals on the tube all by itself. It didn't need any external drivers or anything like that. And that was an important part of the demonstration, that you could do the entire task that needed to be done with this one structure. If it was really a general purpose structure, you should be able to do all of that. So I hooked up the digit lines to the digits on the tube, and I hooked up the segment lines to the segments on the tube, and that's all done. This is a little thing called a prototype board, and all it is a place to stick wires into, and there are
right, all the wires so all the wires in this row here are all connected together. So when it goes to the leg, if you plug any wire in that same row, it'll be connected to the leg. Now these two are different. There's one that has a positive rail, and then one has a negative rail. So all along here, all this bottom row is all connected, all this top row is all connected together. So you can see he's just got one chip. He's got power supply to the chip, and he's got power supply to this thing, the display, and the power supply to the display may be different. But he's probably just got 5 volts on the chip, 5 volts to ground, and that's enough to drive these LEDs, pseudo LEDs.
Are little pieces of metal underneath that connect the wires together. Each of the little wires from the tube is hooked up to the appropriate pin on the chip. We had 6 pins, one for each of the digits to tell you what digit you were on, and there's 7 pins that tell you what segments you should light for that digit. So the purple trace on the scope is the A segment.
So it's
So
strobing.
if you think about the digits, the A segment will be on for everything but 1, which is B and C, and 4, which has those segments, and the rest of the time it will be on. So if you watch the signal here, for the first digit, when we get to 0, there's 1, 2, 3, 4. So that's the way it works for all the digits. It was fun doing this once I had satisfied myself that the chip was actually working, because I had thought through all of these cases and worked them through in my head. And so I had to check out all the places I could have made a mistake, because there was no way to run a simulation through the whole thing all that long.
No, you could have. That's eventually that was the next step at the time. But at the time, you couldn't do it right. You had to do it on paper, and think about it as the finite state machine would be thinking about it, which you can do it all on paper, but it's very arduous. Doing that level of the clock, there's a lot involved, especially if there's no way to simulate on the computer at the time. I'm sure the Defense Department had some stuff to do all that stuff, but he didn't have access to that. So really influential technology, influential person. Doesn't get a lot of credit, but definitely he created trillions of dollars, hundreds of billions of dollars of value in the world just from the VLSI idea. And he jumped ahead, I'd say at least 10 years. This is showing how conceptually chips are made. This is heating up a vat of silicon, just sand, and then but it has to be very pure sand. They cool it, and when it cools, they have this like cylindrical thing that's just a big old crystal of pure silicon. They slice it up, the wafers, and they coat it with some base chemical, and then they take the pattern that he's got here, and they change the surface using ultraviolet to give all the little circuits layer, and they emit a gas that layers down very softly, gently, and it has to be really smooth. Can't have bumps. It has to be really done perfectly, which the LED guy talks about in that LED video. It's crazy how they came up with this stuff. How much just like trial and error. And they eat away with acid. That layer that didn't get exposed, or got exposed, gets eaten away. I can't remember one or the other. Use a lot of UV lasers and light in these processes. It's all photographic stuff, and then they etches up. They have all these different chemical layering techniques I don't know about. All I know is they did a lot of dicking around with a lot of different chemicals for a long time. Where it's like, oh, we got something! Holy crap! A lot of trial and error. And you could build up these 3D structures of these. You got the input lines here. You got the P material. You got the N material. And you got maybe some like this metal bottom here, something under the chemical down here. This is how they build up this stuff. It's pretty nuts. But that'll act like a transistor. Capacitor, I guess. I don't know what that is. They polish it, okay. And they build up bunch of wires and structures. Looks like a big old city. All of the transistors in every little direction down there. That's your chip. Slice it all up. And then put it in a package. And there it is. There's your processor. And all the chips are made pretty much the same exact way. That's how they make them. So these build up these logic gates. So these little logic gates are these symbols. Each one of these little, there's like 8 or 9 or on this one. I don't know. I don't know what generation series he was at. Maybe it's like 1, 2, 3, 4, 5. maybe 8 or 9 on there. And they so these symbols are all built up from that stuff. There's just transistors, and you can put them in a package like this. And that's what each wire would go up. So the input, electrical line comes in here for the signal. And then this is a NAND gate, which will, 2 comes in here. If it's an AND, it'll, goes at the value out here. And you can wire these up to do all those functions just by connecting wires from one to the other. And here's the power, the V, and the ground. And the other one's back here. And that's how it's all wired up to the chip. And here's how the schematic would look. Here's the inverter. It's right there. That whole thing, the actual operation of the thing is right there. So it's V in, what's it called? VDD. So that's where the power comes in. V out is this one, which is like, I hate these words. I wish they would just use 1 or 2 words, but they got to have all kinds of terminology. So this is input, output. Here's the input, here's the output, here's the VSS, which is just ground. I don't know why I have to call 2 different things, but they do. I think it's for this bus stuff, because this will be the allow it to go to 0, so it won't be hooked up to anything, or not hooked up, or definitely hooked up to something. I'll show that bus video. And here's the NAND gate, so it's got the 2 ins here, and it's got the out here, and so it looks almost exactly the same. It's like basically same size, except these pads are bigger. So to make these pads, you have to get more space here. So the more inputs they have to use the space just to connect it up. All right. And there's that 7-segment display we saw in the video. And there's the common cathode. This is what it looks like, the diagrams inside. There's the diodes, the light emitting diodes inside here. So shows how these are all hooked up. These pins here, all hooked up here to a common negative. Okay. And then this is how it works. You have a BCD input. It comes in here. This is the power coming through here. And it's the switches here to decide what the digit is. And it's 0, 1, 0, 0. So in this case, there's only one switch that's down. And that one switch that's down, input line B. So here it is, B, B. B goes output to 1, 1, 0, 1, 1. Or A. So B and C have to be on. Which is which one? It's B and C, right? So it's this one, and then F and G, and B and C and F and G, and that makes that pattern show up on the LEDs. That's how that works. This is how the schematic looks on the inside. This is the naive implementation. It's just like straight out the gate with all the random things that you throw them all together. You got OR gates and NAND gates and AND gates and ORs, and then here is the clever arrangement where it's using just NAND gates and OR gates. And the output is low here. And the reason why it's low is because other equipment that's got the cathode here, this common cathode, expects it to be low to be on. So that's what that means. And the negative means just normally when it's active, it means when it's low, it means that it's the digit 1. So that's all this terminology and like notation. You gotta have to know some of this stuff. I'm giving you this is most of the stuff messed me up.
And then let's try it out by entering some data, because I'm load on 0 through 9, and then after that, the rest of the spots are marked where to go. Up with.
So there's all that. So he's just showing how to implement all these NAND gates and how to do these truth tables. Really great if you want to know how to wire these things up in different ways. Pretty amazing, like, to have this resource available. There's so much out there. It's like having a curated list is like I'm building is super useful to go. Things that will make you go, oh, okay, this is how it works. Not there's like this, does it work like that? It's like, no, it just works like this. And that's usually how all this stuff is. Somebody makes a big deal about it until you go look into it, and then then it's like, oh, it's just that. Okay. So why are NAND gates so special? So the big idea is NAND gates are known as universal gates. NOR gates are also universal, but let's just talk about NAND. NAND gates are universal gates, so you can make other gates out of them. So you could just buy in bulk 10,000 chips of NAND gates, and you can build anything. Instead of having to buy, I need 65 of these and 23 of those, or 14 of those. It's like if you buy the whole bulk, you can get discounts. So that's why they wanted to have a universal gate. Even if it was a little more hassle, you have to use 2 NAND gates to do an AND, or 3 to do an OR, it was worth it. It was worth it just to reduce the complexity of designs and for ordering parts and replacing parts, all that stuff. So, and it talks about here how you can build these things out of these different things, which is this chart here saying the same thing. So this is the AND. It's just an AND with a not at the end. That's it. That's nothing special. And let's see, what was I doing with this one? This one here was designing. Oh yeah, so this is
we want
Ben
to build
here
some kind of outpush of
talking about how to build out this
4 bits.
this
2 and
full on
D3.
that whole thing. He talks about how to
D1 input,
and he actually does it because he goes
Right,
and throws all the wires together, which is a lot of
OR
work.
gates.
This is a lot
Those
of
17
work.
OR gates.
Yeah, so this is a lot of work. So so he goes into how he did that stuff. And useful to know. So that's how they put that together. And there's a side quest here. Is why it's active low. I kind of explained that a little bit. We'll be getting into the microprocessor next. So it's building it all up. You're kind of already there. We're kind of already there.